Welcome to the lecture series on process integration. This is module 6, lecture number 5, and the topic of the lecture is integration of furnaces. Furnaces are frequently used as hot utility systems. That means, it supplies hot utility to the process. These furnaces belong to essential, these are essential components of most process plants. This consumes major energy of the process plant, approximately 75% of the total energy consumption. Tubular furnaces are primarily used for heating all types of hydrocarbons, oils, or used for preheating of air. This shows the diagram of a furnace. Here the burners are there, the oil is fired, these are the flames, and these are the radiation section. This section is radiation section, and the air which goes out from the radiation section has got a temperature TBW. Then it goes to the convection section, where it exchanges heat with a liquid or maybe a gas, and then it comes out and called T stack. Here whatever the temperature here is T stack. Now, if you see the temperature profile of this, we find that the temperature profile is like this. The maximum temperature in this temperature profile is TFT, that is theoretical flame temperature, which is called a adiabatic flame temperature also. The temperature of the air increases by receiving the heat from the burning of the fuel. It reaches to the highest temperature, theoretical flame temperature, and then it goes down when it radiates heat up to this. So, this is the radiation section, and then this is the convection section, where there is a linear temperature profile of the furnace. Now, this temperature profile can be approximated by another temperature profile, which is shown by this red line from this to this. Then there is a sudden jump in temperature, and this is the T effective temperature. So, in the radiation section, we can assume that the temperature is T effective. When it goes out from the radiation temperature, it has a temperature TBW, which is called Breeze-Wald temperature, and then when it goes out of the furnace, then its temperature is called T stack. As a rule of thumb, the heat generated by burning fuel in air can be divided approximately into 3 parts. Part 1 is the radiation chamber, where the heat handle is about 45% to 55%. The second part is the convective section, this one, where the heat handle is about 45 to 25%, and the third section, when it goes out, is the stack section, where the stack and other heat losses take place, and this is about 10 to 20%. So, this is the figure of heat which is being handled by furnace. This is the vertical distance when you go up from here to here, and this is the actual temperature profile of the furnace. Now, this furnace needs to be integrated with the process. Now, when we integrate the furnace to the process, there are major two problems for optimization appears. The furnace integration based on pinch analysis is based on optimization of stack temperature and evaluation of convective section arrangement using capital and energy trade off. Now, when the furnace is integrated, we have to find out what should be the stack temperature. If we want to decrease stack temperature, then more area has to be provided into the convective section. A time will come when the added area will not prove to be advantageous as far as the heat picked up is concerned, and that is why there is a capital and energy trade off in this area. So, this capital and energy trade off will decide what should be the stack temperature. Further, there are also some process parameters and the shape of the GCC which will also predict what should be the stack temperature. So, all these tidbits, all this we will see in the later on in this lecture. The second part is that air preheating system has to be designed, and we have to find out up to what temperature the air preheating should take place. This is also be based on capital energy trade off, and we will see fix that what should be my maximum air preheat temperature and what should be my minimum stack temperature. These are two important parameters which has to be found out based on economic analysis when we are integrating a furnace. Now, the heat supplied by the fuel is QH minimum plus Q stack. What is this? When we are dealing with a process and we are drawing a GCC of the process, from the GCC we calculate what is QH minimum, that is minimum hot utility demand, when a particular delta T minimum has been fixed. So, QH minimum is a function of delta T minimum. So, when we are designing, we are assuming a delta T minimum, and for that a QH minimum can be computed. We have seen in the super targeting that we can optimize the delta T minimum. So, based on that optimum delta T minimum, also we can find out a QH minimum. Now, the fuel which will be burned in the furnace will supply the QH minimum plus the stack losses. So, when we add these two, we can find out what is the fuel requirement in the furnace. Now, if we see what is the QH minimum, QH minimum can be broken into two parts, that Q radiation and Q convection, and combine this together we can say Q ABS. So, the QH minimum is now equal to Q radiation, that means the heat transferred in the radiation section of the furnace plus Q convection, that means heat transferred in the convection section of the furnace. Now, this is a approximated temperature profile of the furnace. Here in the radiation temperature, the temperature is assumed to be constant and equal to T effective, and this is the temperature. This is a constant temperature T effective, and this is the convection section. This is the convection section. So, in the radiation section this gives this much amount of heat Q radiation, and this convection section gives this much amount of heat which is called Q convection, and this is the amount of heat which is called it Q stack, that means stack losses. From the stack the hot gases are coming out at T stack, and this T stack will take with it Q stack amount of heat to the outer atmosphere, and hence it is called stack losses. This amount of is stack losses, and QH minimum is this Q convection plus Q radiation. So, this is the amount which is QH minimum, and this QH minimum has to be supplied by the furnace to the process. Now, if you see the grand composite curve of the process, this is the grand composite curve of the process, this is the pinch point, and this is the hot utility requirement, and this is the cold utility requirement. Now, the furnace profile, because furnace will work as a hot utility, and the furnace temperature profile has to be matched with this grand composite curve for a better heat transfer or meeting the hot utility demand at the lowest cost. So, here we see this is the hot gas temperature profile which is in the furnace. The highest temperature of the hot gas in the furnace is TFT, that is theoretical flame temperature. Then it comes down to a temperature of atmosphere. So, this is the loss, that is stack loss, and this is the amount of fuel in terms of enthalpy required to generate this curve. Fuel gas profile is shown in the figure by a constant heat capacity flow rate Cp line, and the slope of this fuel gas temperature profile is depends upon the capital Cp, that is heat capacity flow rate of the hot gas, because the slope of this line is 1 by capital Cp or 1 by heat capacity flow rate. Now, this links the TFT to T0. So, this line, the one extreme is TFT, the other extreme is T0. In convection section, the tubes which are often finned are mostly arranged as coils across the direction of the flow of the flue gas in such a manner that this can be considered as overall counter current heat exchangers. Now, this figure will like to find out if I am representing my fuel gas profile with this line or the fuel gas profile with this red line, what is the difference? Now, we have seen that in a furnace what is the actual temperature profile. That actual temperature profile can be represented in two ways. One way is this and another way is this red line. So, this is the approximate temperature profile of the furnace. Now, this is the process GCC, and here there is temperature T stack, this point, and this is the pinch point. So, this line can move up to the pinch point. It cannot go below the pinch point, but it can move up to the pinch point. So, if it moves in this direction, the stack losses will decrease. That means, if the angle, this beta angle is less, then it will be stack losses will be less. So, the question is now whether to represent the hot utility temperature profile by this line or by this red line. Now, this can be clarified by Peter et al. As shown in figure A. In this figure, the furnace flue gas temperature profile is shown in two ways, through a straight line and B through an approximate profile. Approximate profile is this and straight line is this. The study shows that the difference between these two treatments in volumetric flow rate of gas is only 1.7%, and in terms of fuel consumption it is only 2.6%. So, for all practical purposes, the straight line assumption of the flue gas temperature as shown in figure B, this is the figure P, this is the straight line representation of flue gas temperature profile can be accepted. So, when we prove that this temperature profile creates very less error as compared to the other temperature profiles or actual temperature profiles, then for rest of this lectures, while doing integration, we will presume that this temperature profile of the furnace works well. Now, this is a case when this is the pinch point, and up to this pinch point the stack temperature is not able to reach due to this portion of the GCC. So, the process GCC is now controlling the stack temperature. So, if such a situation is there, then obviously the stack temperature will be far more than the process pinch point. It can be more than the acid dew point also, and hence a lot of stack losses will take place. And in such a cases, what we can do to decrease the stack loss, we can preheat the air with the heat which is available with the hot gas, and can thus improve the efficiency of the furnace. Here this line is being controlled, the slope of this line is being controlled by the pinch, because it is touching the pinch, and TDP is here, acid dew point. At this point, I would want to clarify that the stack temperature can be brought down up to TDP, not below this, because if the stack temperature is below acid dew point, then the whatever acid component of the gas are present in the flue gas, maybe due to the burning of sulfur, those will condense and they will form acid, and this acid will attack the stack or the heat exchangers, and hence it is not advisable to bring down the stack temperature below acid dew point, that is TDP. In this case, the TDP is below pinch, and I can bring down the stack temperature up to this, but this pinch point is controlling. it will not allow me to bring down the temperature. Here also there is a chance that I can use the stack for heating, that means whatever the temperature of the stack gas that can be utilized for heating or preheating of the air. Now, there is a third case when TDP is above the pinch, and in that case I can bring down the stack temperature up to TDP only, I cannot go below TDP because it is not allowed. So, here we have seen that process GCC is controlling the stack temperature. Here we saw that the pinch is controlling the stack temperature, and here we saw that the AC dew point of the flue gas is controlling the stack temperature. So, this three situation may arise when we are integrating the furnace with a GCC. Now, let us build the model equations for the furnace. If we take the heat balance around the furnace to find out the actual flame temperature. Now, this temperature depends on many factors such as calorific value of the fuel, the construction of the burner and its type, heat loss due to incomplete combustion, heat loss to ambient, and the extent to which the combustion product dissociate. So, these are the factors which will decide what is the actual flame temperature. Now, to quantify all these factors beforehand is difficult, and hence to calculate actual flame temperature is difficult in a furnace. So, we will substitute it with another temperature which is theoretical flame temperature. From the heat balance we can write down this MF into HC is equal to H fuel plus H air equal to H FG plus H CHFG plus H loss plus H dissociation, where Hc is the standard heat of combustion of the fuel with air to create flue gas. H fuel is the enthalpy of the fuel, H air is the enthalpy of the air, H Fg is the enthalpy of the flue gas, H CHFG is the enthalpy loss due to the mechanical and chemical regions in the combustion zone resulting from the incomplete fuel burn up. H loss is the heat loss to ambient, and H dissociation is the enthalpy loss resulting from the dissociation of the flue gas. So, the parameters which are involved in predicting the actual flame temperatures we have written here, and many of these factors are unknown or difficult to find out, and hence when calculating a theoretical flame temperature we will set them to 0. Now, for fuel enthalpy, H fuel can be written as MF, the mass flow rate, plus CPF, the specific heat of the fuel, T fuel minus T 0, where we have taken T 0 as the reference temperature. Similarly, enthalpy of the air we can calculate H air is equal to Ma, mass flow rate of the air, Cpa into T air minus T 0, where T 0 is the reference temperature. Enthalpy of the flue gas can be similarly explained, MFG, mass flow rate of the flue gas, in CPFG and TFT, that is theoretical flame temperature minus T 0. So, because we are interested in calculating theoretical temperature, now all the computations will be based on theoretical flame temperature rather than actual flame temperature, where MF, Ma and MFGs are the mass flow rates of the fuel, air and flue gas respectively, and CF, Cpa and Cfg are the specific heat of fuel, air and flue gas respectively. Now, let us assume something stoichiometrically air to fuel ratio is RAF and EA is the fraction of RAF required as excess air to have complete combustion of the fuel. It is generally done that the stoichiometric air is not able to do the complete combustion of the fuel, and hence we increase the amount of air to have a complete fuel combustion. And what is that increase in the amount of air? In general, excess air requirements for gaseous fuel is about 10%, liquid fuel is about 15 to 20% and that of solid pulverized fuel is more than 20%. So, if I do this two terms I include, and based on these two terms I can write down now the actual mass of air which will be required after including the excess air is this MF RAF plus RF into EA, which is the extra fraction of the RF required to have complete combustion based on this percentage. So, we can express MA as equal to MF 1 plus EA into RAF. Similarly, MFG, which is a summation of MA and MF, can be written in terms of MF with this expression. Now, the actual flame temperature TTFT is difficult to calculate. The actual flame temperature is not TTFT, actual flame temperature is difficult to calculate and thus theoretical flame temperature, that is called adiabatic flame temperature, can be computed by considering CHFG and H dissociation to be 0. Actual flame temperatures are about 10% lower than the theoretical flame temperature considering complete combustion. Then by energy balance we can write down HFG, this is enthalpy of the flue gas, is equal to T TFT minus T 0 into CPFG into MFG is equal to MFHC plus H fuel plus H air and minus HCHFG minus heat loss minus H dissociation. So, these two terms we are setting to 0 because I am thinking that this is a ideal burning of fuel takes place and that is why these two terms are 0. So, whatever temperature we will calculate based on this will be the theoretical flame temperature. So, TFT is equal to T 0 and this. So, TFT minus T 0 equal to this will go this way division by this. So, in terms of excess air this is the temperature. So, here I am reproducing again MA is equal to this in terms of MF and MFG is equal to in terms of MF. So, air to fuel ratio is RAF and EA is the fraction of RAF required as excess air to have complete combustion of fuel. CHFG is the enthalpy loss in the combustion zone resulting from the incomplete fuel burn up and H dissociation is the enthalpy loss resulting from the dissociation of the fuel gas. Now, taking process to be adiabatic, H loss becomes 0. So, again I set H loss equal to 0 and let us assume that KFG is equal to 1 plus 1 EA RF into CPG. This we are this whole term is being represented by KFG and this whole term is now represented by k here, and if I substitute this, I get a relationship like this: T f t equal to T 0 plus H c plus C p f T fuel minus T 0 plus K air T air by minus T 0 divided by K f g. Now, if I consider there is no fuel preheating, in general fuels are not preheated due to the safety reasons, and if I consider that, then the T fuel will be equal to the T 0, that is the ambient temperature or the reference temperature, and hence T fuel minus T 0 will tend to 0, and T f t, which is the theoretical flame temperature, will be this equal to. So, we started with actual flame temperature, then one by one we set those parameters which are difficult to calculate. Then we consider that the process is working as adiabatic, that is H loss is 0, and from that we are able to find out this temperature which is T T f t, and which is a theoretical flame temperature, and basically it is called also adiabatic flame temperature. So, and all our calculations and processing or of integration of the furnace will be based on now this T f t, which is the theoretical flame temperature, and this is called theoretical flame temperature. Now, let us see if you are doing integration, then this A is the approximate fuel gas line, this is approximate flue gas line, and B is the single flue gas line. And we have seen that if we are going for a single flue gas line, we are not committing much of a mistake. Now, from this we can write down that this tan beta is equal to Q radiation this much or this much, Q radiation divided by T f t minus T b w. Now, this distance, this T b w and this is T f t. So, this is the distance. Okay. And Q radiation is this from here to here, this is Q radiation from here to here. So, tan theta is equal to this distance Q radiation divided by this distance from here to here, which is nothing but T T f t theoretical flame temperature minus T b w. So, when we take beta, this is arc tan Q radiation divided by T f t minus T b w. Similarly, we can find out that this beta is equal to fuel divided by T f t minus T 0. So, this is the fuel which has been consumed in this. Now, this distance which is fuel divided by this distance which is T f t minus T 0. Similarly, this beta is also equal to arc tan Q h minimum, this is Q h minimum, this is Q h minimum divided by T f t minus T stacked. So, this is the stack temperature. Now, this distance from here to this point is T f t minus T stack, and this whole distance is basically Q h minimum. So, these relationships we can write down. Now, the breeze wall temperature, because it involves breeze wall temperature here, the breeze wall temperature can be computed as x into T effective minus x minus 1 into T F T, whereas where x is the degree of stirring and depends on the type of furnace, size and layout of tubes in the radiation section, type of fuel used, emissivity of the different surfaces, etc. The value of x is equal to 1.03 for horizontal and vertical fired heaters. So, knowing the value of x and T effective and TFT, we can compute the TBW value. Now, computation of Q radiation and Q convection. Now, Q radiation can be given by this formula and Q convection is given by this. So, this is the Q convection area, because in the convection this temperature drops down from here to here. So, this is the distance which is given by Q convection and this is the distance which is given by Q radiation. So, we can calculate this, and T S out is the temperature of the flue gas leaving the convection section. This is the T out, T S out, which is leaving the convection section. Now, Q H minimum is equal to Q radiation Q convections, and we can develop a equation for that or expression for that. So, this is the value for Q H minimum. Now, let us assume Q F G equal to this and Q R equal to this. So, we can substitute the values here and we can have Q H minimum equal to Q F G M F in the brackets T F T minus T S out. The combustion air at T 0 ambient temperature is preheated to a temperature of T air when we are doing the preheating of air. The flue gas preheat the air from T 0 to T air, and doing so the temperature drops from T S out to T S, which has to be kept higher than the AC dew point temperature T D P. Now, what does it mean? That if the air, that is flue gas, is coming out at T S out and the T S out is a higher temperature than T D P, that is AC dew point, I have already told that the flue gas temperature can be brought down up to T D P or a little bit more than the T D P, so that the acid vapors which are present in the flue gas do not condense. And obviously, if they will condense, they are going to erode the metal part of the equipment which is handling this. So, T out can be brought down to little bit more than T D P or say theoretically equal to T D P, and this can be used for preheating the air. So, after preheating the air, if the T S out becomes T S, then this T S should be more than the T D P. So, heat balance for air preheat. So, K F G into M F T S out minus T S. So, for heating the air, I am bringing down the T S out temperature to T S. It is M F K R T air minus T 0. Air is entering at T 0 temperature and it is being heated up to T air temperature. So, M F cancels out, we can write down this. Now, Q H minimum is K F G M F T F T minus T S out, this we know. From the above equation and substituting the value of T F T minus T S out, I can find out this, which is the M F, which is the mass of the fuel, is equal to Q H minimum divided by H C minus T S minus T 0. into KFG, or I can write down MF is equal to QH minimum HC double dash minus this value. Now, HC double dash is the practical SC value due to the energy losses in combustion chamber due to the mechanical and chemical reasons resulting from the incomplete fuel burn up and enthalpy loss resulting from the dissociation of the flue gas. These losses are of the tune of 1 to 3%. Thus, the HC double dash value is 1 to 3% less than the HC values. So, if I put this here, I will be able to estimate the actual value of the mass of the fuel which will be required. And why we want this? Because for the economic calculations or the trade off, I should know the what is the mass of the fuel, because the cost of the mass of the fuel has to be added up. Now, let us come to the stack temperature optimization. I had earlier told that we have to decide a stack temperature, and this decision will be based on trade off. Stack temperature optimization is carried out based on optimal total annual cost, which includes fixed cost, that means cost of area in the convection section, and operating cost, which includes the fuel cost. Now, this is my system. From here to here is the radiation section, this temperature is TBW, and this is the convection section. So, I am interested in finding out what is the T stack temperature, which is the temperature here of the hot gases which is coming out, and this is the my convection section. And so, there are heat exchangers available in the convection section which exchanges heat with this hot gas. So, I should know about these heat exchangers, their area, so that I can compute the cost of these heat exchangers. Now, this is the convection section and this is my temperature profile. This is the temperature profile in the radiation section and this is the temperature profile in the convection section. So, what will be my algorithm? Determine the theoretical flame temperature. This I know, we have developed expressions to calculate this is theoretical flame temperature based on combustion of the fuel without air preheating. As a starting point to determine the flue gas line, using the grand composite curve GCC, determine the lower boundary of the temperature interval of T stack and evaluation of the minimum value of the fuel consumption. This is fuel minimum. So, I am integrating the furnace with the GCC. So, the furnace part comes from here and the GCC part we have to add, and GCC part will decide what should be my minimum stack temperature. So, here it shows clearly that if it is the line available, I can broaden this line to here, when this pinch point will control my T stack temperature. So, this is my range is from TBW to this pinch point, and here the pinch point is above the TDP. If this TDP will be above the pinch point, then the TDP will control the T stack rather than this pinch point, and this is the fuel minimum. If it is, this is that line of the furnace flue gas. So, this is the loss, stack loss, and this is the QH minimum. So, the minimum fuel will be equal to QH minimum plus the stack loss. So, I can calculate fuel minimum here, this amount from here. So, this T stack has to be optimized and I have to find out a value of this T stack based on the optimization. Now, determine the heat transfer in radiation chamber and the breeze wall temperature TBW, which is the temperature of the flue gas leaving the radiation chamber, and the equation is this. I had already explained this equation where the x value is around 1.03, and then perform various computation taking the different values of T stack. So, what we have to do, determine the heat transfer in the convection section. So, if I know the TBW, this is the point, I know TFT, this is the value, and this is the Q radiation. So, if I know this angle, I can find out this Q radiation amount, or this is the gap between this point and this point. So, I know Q radiation, I know QH minimum from the GCC. So, I can find out Q convection, and once Q convection is available to us, we can design a heat exchanger which will transfer Q convection. So, we can find out the area of the heat exchanger which is in the convection section, which can transfer Q convection, and this is the Q convection from here to here, and this is the flue gas line in the convection section. Then determination of annual cost of the fuel burnt, we can calculate the amount of fuel which is required, that is minimum fuel which is required from here, and we can do the costing of that fuel. This is fuel minimum. So, fuel cost is known, and from the area in the convection section we can find out the annualized capital cost, and then we can add them together to find out the total cost. Now, please refer to the lecture on cost targeting to determine the annual cost. If you are not able to understand, refer to this lecture cost targeting, where it is very clearly given how to calculate the TAC, that is total annual cost. Now, this is the total annual cost, this is the hot utility cost, that is the cost of the fuel, this is the annual capitalized cost, this depends upon the area of the convection section, this is the annual operating cost of the convection section, and when we add them together, this is the total annual cost which we get. So, the minimum point we can pick up, and then we can draw a line, we can vertically draw a line to this perpendicular to this axis, that gives me T stack optimum. So, if I keep the value of the T stack at this point, then the total annual cost of operating the convection section will be minimum. So, this is how T stack is optimized, and once the T stack has been optimized, then I can optimize my T air temperature, that means optimum of temperature of the air up to which it should be preheated. Now, the next is optimization of air preheat temperature, which is T air. If the combustion of the air is preheated by keeping the air to fuel ratio constant, the theoretical flame temperature in the furnace will increase. This we know that if we keep the air to fuel ratio constant and start preheating the air, the theoretical flame temperature will increase. This shows this will change the slope of the flue gas line, Cp of the flue gas line will decrease, and thus the slope will increase and the stack loss will decrease. Now, say this is operating at this T stack. Now, I start sending the preheated air to the furnace. So, what will happen? This TFT will increase. Once this TFT increase, I have to pass through this stack temperature, optimized stack temperature. So, this will somewhere come here. So, the stack losses will be less. So, we will let us see here. This is one line, a little bit of TFT has been increased. So, a little bit less stack loss. Then the second comes here, a bit of TFT has been increased. So, stack loss has decreased, and in this third part, when I am increasing the TFT far more, the stack loss has decreased, and the the angle is also changing, it is decreasing. So, this says that this will change the slope of the flue gas line, Cp of the flue gas line will decrease and thus its slope will increase. The fuel requirement will decrease by the amount of heat picked up by the air during the preheating before combustion. Now, if I am preheating the air, then obviously there will be a saving in the fuel, and how much saving? That the amount of heat which will be picked up by the fuel, amount of heat which will be picked up by the air before the combustion. So, what we found that when we are heating the air, this TFT is increasing, and once TFT is increasing, we have different lines here, and based on the slope of the lines we can find out what is the Cp value of the gas line. If the Cp is more, the slope is less, and if the Cp is less, then the slope will be more, because it is 1 by Cp. So, now if we see here this place, now the T air can be heated up to a point which is called T air max. Basically, the T air will be heated up from the T 0 here, this is the T 0 point to T max, and this T max will be little bit less than the TDP. So, the air preheat can be done utilizing exhaust flue gas. Now, this air preheating can be either be done by using the exhaust heat from the flue gas, or it can be heat by the lower pinch area of the GCC. So, this is also a heat source, it can be heated by this or it can be heated by both. So, this basically this T 0 is here. So, from T 0 to T air it can be heated up by the flue gas or by the lower pinch area, because this is a heat source. So, here the MF, this fuel requirement can be computed from here, QH minimum divided by HC double dash minus Ts minus T 0, where Ts is the temperature which this T stack will acquire after it gives heat to the air, and this Ts cannot be less than this TDP. Now, what we see that the variation in the mass of the factors that are affecting the fuel consumption, variation in the mass of combustion air supply, this will also affect, and when this is affecting, basically when the mass air of the mass is changing, basically this slope will also change. Variation in the combustion air temperature, if the combustion air temperature is rising, obviously there will be a decrease in the fuel amount, and variation in the fuel temperature. Basically, variation in the fuel temperature we are not doing, because due to the safety reason we are not heating the fuel, we are only heating the air. Now, from this figure we can write down the QR max, that the maximum heat which can be pushed to the air for preheating is this Cp Fg T stack minus TDP. That means, T stack can be brought down to up to the TDP, not less than that I have already explained why this should not be done, and this is equal to Cpa Tr max minus T 0. That means, from T 0 to Tr max this can be heated up to this, and obviously Tr max temperature will be little bit less than the TDP, or maybe to be calculated based on the economic analysis, because this is a counter current heat exchanger, this is in this direction, this is in this direction. So, how this will be done? Let us assume that the T stack optimum is known from the section of optimization of T stack. So, we have already shown that how the stack temperature can be optimized. So, after we do the optimization of stack temperature, we know the T stack optimum value, and if this temperature is higher than the AC dew point TDP, then there is a chance of heating the air by the stack gases which are coming from the stack. Now, if it is so, then my T air temperature will be within this limit T r maximum and T 0. So, within this limit I have to find out T air optimum. Now, this T air optimum means up to the temperature up to which the the temperature of the air should be increased will be calculated based on optimization. Now, if you see the heat transfer to the air in the convection section, we can write down Q air is equal to U into A air into delta T ln log mean temperature, and the capital cost of the heat exchanger which will have A air, that means area, can be computed by this equation, where A plus B into A air, that means area of the heat exchanger which is heating the air to the power C. Now, the annualized capital cost equal to annuity factor into capital cost of the heat exchanger having area A air. So, this is the capital cost. We have to multiply with the annuity factor to find out annualized capital cost, and that annuity factor is this. So, this is the annuity factor, this is the N, that is the lifespan of the heat exchanger, and this is the interest rate I into capital cost, and then the total annual cost will be the annualized capital cost which will be computed from this line plus annual operating cost which is the cost of the fuel saved per year. So, this is the capital cost line of the air preheater, and this is the fuel cost, it goes down. So, more is the capital cost, less will be the fuel cost. So, I will get a optimum value here somewhere. So, this will give me T air optimum. So, what we have calculated? We have calculated T air optimum and T stack optimum both, and this is the requirement. When we started our lecture, we told that when we are integrating the furnace with the GCC, these are the two pertinent parameters we have to calculate, that is T stack optimum and T air optimum, and these two parameters were computed based on the capital cost energy trade off. So, these are the references. Thank you.